Hello students, in the previous class we have read about the Gauss's law, and in today's class we will read application of Gauss's law. So, for some symmetric charge configuration, it is possible to obtain the electric field in a simple way using the Gauss's law. If these simple configurations are uniform shapes, then the calculation of Gauss's law becomes more easy. So in the section, what we are going to see is the calculation for the uniform shapes such as a wire, then a plane, and lastly a volume containing sphere, a volumetric area, like a volumetric diagram or something which contains volume, and there is no better example than sphere because sphere shows uniformity. Now we'll go to the first one. Field due to an infinitely long, straight, uniformly charged wire. This wire is uniformly charged. Throughout the wire, charge distribution is uniform, and this wire is infinitely long. This is going up to infinity, minus infinity, plus infinity. So we will see case in this when we are having a infinitely long, straight, uniformly charged wire. Now consider an infinitely long, thin straight wire with uniform linear charge density lambda. Charge density lambda is defined for wires, defined for straight line or wires, and it is defined as lambda equals to the small q contained in the small part of length of the wire, small part of the length of the wire. Now if we are considering the whole charge on the whole length, we can write q upon L. So if we want to know what is the charge present, we can multiply our linear charge density with the length of the given wire to know the charge. The wire is obviously an axis of symmetry. What does an axis of symmetry implies? This is our y, from this is our wire, and this plays as the axis of symmetry role. From this particular wire, anywhere, if you take at this point or this point, the distance will be same, thickness will be same, and if you rotate it, the imaginary cylindrical formation which is happening over here will have the same radius. Here, 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 everywhere radius of the cylinder is same. Now taking the radial vector for O to P and rotating over point P, P dash, P double dash, which are completely equivalent with respect to the charged wire. This is our charged wire. This is our charged wire. Okay. And in this charged wire, we have taken a point P dash, P, and P double dash. From the center, from here, the center O, this distance is R, this distance is R, and this distance is also R. So they are saying they are completely equivalent from the center. This is why we are saying that our straight wire is axis of symmetry. Complete equivalency is shown over here. Direction of electric field at every point must be radial. Radial implies this is our end of our wire. Okay, end of our wire will look like circle. Why so? see, when we extend it, it looks like a cylinder. The wires are solid cylinders. Wires are solid cylinders with very minimum of radius. Very minimum of radius. So what is the case? Case is that this is circular. So circular will give fields, electric fields in this direction, this direction, this direction, this direction, like all the possible direction. So once we draw these electric field lines from this surface, what we can see is these are radially expanded out, radial E, radial E. Okay. So direction of electric field at every point must be radial. Now outward, this, it is radial for any case, but it will be outward when the charge density is positive, and it will be inward when the charge density is negative, charge density is smaller than 0. Consider a pair of line elements P1, P2 of the wire. Electric field produced by the two elements of the pair when sum gives a resultant electric field which is radial. The components normal to the radial vector cancels out. What the statement suggests us is that we have to consider a line element P1 and P2. See over to the diagram here. This one is P1 and this one is P2. So the electric field produced over this point and over this point are radial, one thing we know, and secondly, for this point it will be somewhere like this, and for this point it will be like this. So the normal components over here, the normal components, normal implies the component which aim at making 90 degree with each other. That kind of components of radial vector, what will happen to this? They will cancel out, they will cancel out. Since the wire is infinite, there is no end of the wire, no start of the wire. Wire is infinite, it's long, very long, extremely long. Electric field does not depend upon the position of P along the length of wire. So when the wire is very much long like this we are having, okay, so over here, over here, or over here, we can keep point anywhere, it does not matter because it keep on extending. If you will see from here, you will find P is here, and from here if you will see, you will find it is okay, the distance x1 and x2 from this end and from this end is both equal. So there is no need for like understanding it or precisely putting it at the center. In short, electric field is everywhere radial, in the plane cutting the wire normally, and its magnitude depends only on the radial distance r. How much far is the point P is, that will define the magnitude of E. We have seen further we move from the charge, lesser is the electric field strength. Further we move from charge Q, less is the electric field strength. Why so? Because it also follows 1 by r square relation, that is inverse square law. Now we'll come to this point. Point number 3 on the same slide. To calculate field, imagine a cylindrical Gaussian surface. Since the field is radial everywhere, flux through the two ends of the cylindrical surface is 0. Why 0? So for understanding that, let's come to the figure here. Figure. This is the direction of our wire. Wire is in this direction. Here plus infinity and here minus infinity. Now this distance is r. This distance is r. Here also and here also. Electric field direction is this. Electric field are moving from here to here. See, this is the direction of electric field. Now if we consider this phase, if we consider this phase, what is the angle, or like what is the direction of surface vector, surface area vector? Surface area vector will be in this direction. Surface area vector gonna be in this direction, and electric field is in this direction, E. What is the angle they are making? They are making 90 degrees of angle. So what we know, electric flux equals to E dot S equals to ES cos theta equals to ES cos 90. So when we have taken 90 degrees, cos 90 will be 0. So it will turn out to be 0. The whole thing will turn out to be 0. Now when we will go for the phase 2, this one, the similar condition arises for this. The surface area vector is in the downward direction and our E is going in this direction. Here also E and S are making an angle of 90 degrees. As cos 90 is 0, the flux through this point will also be 0. But when we see the curved surface area, the area in yellow, this is the curved surface area of our cylinder. Okay. So in this, the area vector, where is the area vector moving? Area vector is in this direction, in this direction. In this direction. S is in this direction. What about E? E is also in this direction. What is the angle they are making? Theta equals to 0. What is the value of cos theta? Cos 0, that is 1, and hence maximum flux will come out from this curved surface area, that is ES. Then we will substitute the various values here to find our result. Moving to the next point. See, I'll go with the first point here. See the blue lining. To calculate field, imagine a cylindrical Gaussian surface. Since field is radial everywhere, flux to the two ends of cylindrical surface is 0. This and this will give us 0 flux, and only this surface will give us maximum flux. At the cylindrical part of surface, E is normal to the surface at every point and its magnitude is constant since it depends only on R. E is dependent only upon the R, the radius of the Gaussian cylindrical surface. The surface area of the curved part is 2 pi RL. 2 pi RL. Where L is the length of the cylinder, this particular length. See over here, this length is L, length of the Gaussian surface which is cylindrical in form. Now flux to the Gaussian surface will be flux to the curved cylindrical part. Actually the flux will be taken as flux through surface 1 plus surface 2 plus surface 3. But we have seen flux to surface 1 is 0, flux to surface 2 is 0, and we have only flux from the third surface. Hence, from the third surface, how much flux we have? It is E into S. Here S ka value is 2 pi R L. So we will substitute over here E into 2 pi R L. That is what we have done here. So flux here will be given by E cross 2 pi R L. E cross 2 pi R L. The surface includes charge equal to lambda L. How did we get that? We get it from the linear charge density, already explained in this slide and even in the previous slide. Linear charge density is defined for a length or a wire and it is denoted by lambda. Lambda is equals to charge upon the length of the wire and the SI unit for this is coulomb per meter. So from here we can find the charge by rearranging these. We'll get charge equals to linear charge density into the length of cylinder. So this is what the amount of charge we are having in the Gaussian surface. Gauss's law then gives us E cross 2L equals to 2 pi R L equals to lambda L by E naught. How does we get this? We get this from flux is given by E S as well as flux is given by 1 upon epsilon naught into Q. So these two values, these two equations gives us the equation for flux. Now we are equating both the equations. Equating both the equations. And what we will get? We will get ES equals to 1 upon epsilon naught into Q, where E will remain E, surface area will be 2 pi R L, epsilon naught will be epsilon naught and Q will be lambda L from this equation, Now L and L will cancel out and we will be given the value of, I'll cancel the L with green, L will cancel out with L and E will be given as lambda upon 2 pi epsilon into R. That is the value and this is not depicted vectorly, okay, not depicted vectorially. So how do we do the vector depiction? E vector equals to lambda 2 pi R into n cap. This is not n cap, this is r cap. This is the unit vector for direction, unit vector for providing direction of the position vector. Now r cap, radial unit vector in the plane normal to the wire passing through the point E is directed outward if lambda is positive and if lambda is negative it is directed inward. The assumption the wire is infinitely long is crucial. Without this assumption we cannot take E to be normal to the curved part of the cylindrical Gaussian surface. However, above equation is approximately true for electric field around the central portion of the long wire where the end effects may be ignored. What these two line implies is that it is very much necessary for us to take the wire to be infinitely long. Secondly, if we say that our wire is extremely long, but we are not saying that it is infinite, our wire is extremely long. In such cases, this application of Gauss's law application of Gauss's law shows validation near the center of wire. वायर के बिल्कुल बीचों बीच the application of Gauss's law will be valid. Why so? Because at the central part of the wire, end effects may be ignored. First thing which we have seen so far is the electric field. Electric field, here we are calculating. We have seen, right? We have been calculating electric field. So what sort of electric field we are calculating? We are only considering E due to Q, which is present only inside the charged body. There are Q which are present outside and they also influence E. Also influence E, but it's not been considered. Okay. So that is one thing, and in the I'll just summarize it how we have derived. I'll make a graph like a diagram, and then we will move to the next part of the same topic. So what we are looking here is application of Gauss's law, and the case we have considered is a case of infinitely long wire. Infinitely long wire. Infinitely long wire. So see the diagram over here. This is our wire. This is our wire. I'll just make it once again. It is not coming good. Okay. Okay, so this is our wire. It is a little misshaped, so we'll just try to make it in a shape so that we are getting a good diagram. So this is the wire we have got. This is having positive charge or negative charge. It can be anything, but for our convenience we are taking, let the wire is having a positive charge distribution over it. Then for knowing how Gauss's law is applicable on this wire, we will make a charged a Gaussian surface. So wire is kind of a cylinder, so the Gaussian surface which will be made on this will be cylindrical in nature. Okay. So this is how we have made a cylindrical surface over here, and this red color thing is our Gaussian surface. I will just color it. This is one surface and this is the other surface, and then this is the third surface. This is the third surface. I am roughly coloring it so that you will understand it. So this is our third surface. Why I am defining it with all these colors is that so that you understand which surface we are talking about. Now first thing is that when we are defining such thing, this is our line. This is a line. This is a wire which will have linear charge distribution, which will show linear charge distribution. For linear charge distribution, we have our linear charge density, linear charge density. That linear charge density is denoted by lambda and is given by charge upon the length. Equation number 1. From this charge upon length, we can find the value of charge in terms of linear charge density, which is given as lambda L. So this is our equation number 2. Now the electric field, what is the direction of the electric field? This is the direction of the electric field. They are moving from your right to your left or from your left to right. You can take any direction. So they are not along the direction of the wire or along the length of wire. E is not along the length of wire but is perpendicular to length of wire. You can see the length of wire is in this direction, whereas electric field is in this direction. Now the surface area vector from this point will be in this direction, like this. This is the surface area vector. These are the electric field vector. So area vector, electric field vector, E S. What is the angle they are making? 90 degree. So flux at surface 1 equals to E dot S equals to E S cos theta equals to E S cos 90 equals to 0. Similar is for xi 2, that is 0. The surface over here, it is moving in this direction S. So S over like this and E like this, E S, making a 90 degree angle. So but here the surface is over here which is having the same direction as of the E. Both are parallel. So the theta over here is 0 degree. Now we will find flux through Gaussian surface. Flux through Gaussian surface, that is xi, and it will be given as xi equals to xi1 plus xi2 plus xi3, and here xi equals to 0 plus 0 plus Es cos 0, that is Es. Secondly, we know that flux equals to Q upon epsilon naught. Here from equation 2, Q equals to lambda L. Let this equation be 3. So xi will be equals to lambda L upon epsilon naught. This is our equation number 4. Equating 3 and 4 equations, what we will get? We will get E into S equals to lambda L upon epsilon naught. Then surface area of this cylinder will be this, only the surface area, which is given as 2 pi RL equals to lambda L upon epsilon naught. Here L will cancel out and we will be left with E equals to lambda upon 2 pi R epsilon naught. So here if we are writing this in the vector form, we have to introduce the unit vector for the radius. So this is the electric field passing through a wire of infinite length, and we have found it out using the Gauss's law and the Gaussian surface. Moving to the next application, field due to uniformly charged infinite plane sheet. When we are talking about the plane sheet, we are considering some area, okay. So this is our I'll just change the pen color, wait a minute, yeah, this is our plane sheet. This is our plane sheet over here, and we have to consider the electric flux through this plane sheet. On the surface of this plane sheet we are having charges, and we have to consider the flux on this particular plane sheet. For that we have just colored it. Now we will understand where are the axes. See, axis Z is over here and axis Y is over here and x-axis is over here, see. And then we have introduced a Gaussian surface. We have introduced a Gaussian surface which is along the x-axis. This is the Gaussian surface we are talking about. And see, this is along the x-axis, not along y-axis, not along z-axis. So the flux at the other faces which are facing z-axis and y-axis will be 0. Like this particular face will show 0 flux, then this particular face will show 0 flux. Only the face which will show the flux are this one face and the opposite face, opposite of this, okay, they will only show the flux which are along the x-axis. So face 1 and 2 will give us flux, and face 3, 4, 5, 6 will not give us any flux due to them will be 0. And fluxes along like electric field lines, we are talking about electric field lines which are along the x-axis. Now we'll just read it out what we have for the derivation, how we are deriving it. Let sigma be the uniform surface charge density. From where does this surface charge density is coming? We have already introduced in the previous class. The surface charge density is given by sigma, and it is the charge contained in the area element. This is the formula, and from this formula, similar as we did previously, we will find the charge. Charge will be given as surface charge density into the surface. We take x-axis normal to the plane. This is our plane, and x-axis is in this direction. So see, they are normal. By symmetry, the electric field will not depend upon y and z coordinates, and its direction at every point must be parallel to x direction. At every point, electric field will be like this. This will be the electric field, this will be the electric field. So these are what? They are parallel. Parallel to each other and parallel to x-axis. See, I'll write over here E parallel to axis. Gaussian surface taken over here is a rectangular parallelopipe. Parallelopipe implies something which looks rectangular and is kind of parallelogram but forms a pipe. Okay, you can just imagine a pipe having a rectangular shape of cross-sectional area A. The cross-sectional area of this parallelopipe is A. Only phase 1 and phase 2 will contribute to the flux. Electric field lines are parallel to the other phases and therefore do not contribute to the total flux. The net flux to the Gaussian surface is 2E. Charge enclosed by the closed surface is sigma A. Therefore, by Gauss's law, 2E equals to sigma A epsilon naught, E equals to sigma upon 2 epsilon naught is the electric field, the amount of electric field we are having. So, the concept which is not clear over here is how do we get 2EA and sigma A. Sigma A we are getting from the charge density formula. Charge density formula. See up on the slide, I will just mark it with the green, this. From here we are getting this, okay. And this 2EA, how we are getting, I will explain it. Just watch that one so that we get a proper idea how we are defining the flux for the surface 1 and surface 2. So, see over here, this is our surface, the plate we have taken so far, like with area element A, this is our surface. And this is blue colored thing is our Gaussian surface. Blue colored is our Gaussian surface. Okay, so as we have stated, like our one axis is in this direction, other axis is in this direction, and the third axis is here in this direction. This is y, this is z, and this is x. We have assumed our electric field lines are coming like this, E. E is coming like this. This is electric field line. Now, what is the alignment of the surface area with respect to electric field line? This is our phase 1, phase 2, 3, 4, 5, 6. These are the phases. So, phase 3, 4, 5 and 6 will not play any role in the flux contribution. So, flux from these phases will be 0 because this surface area from this third surface will go up, which will be 90 degree to electric field. This and this will have theta equals to 90 degree. From this surface it will come in this direction and electric field is over this direction. They are also making 90 degree. Simpler, here from here it will be like this and this electric field will be like this, E and S. From here S will go like this and E is going like this. So, they are also making a 90 degree. Just see this angle in a 3-dimensional view. Don't just see according to the plane of paper. According to plane of paper, this looks just like some 30 degree. But if you see like it is going straight and this thing is going in this direction, they are making a 90 degree. So, they all from phase 3, 4, 5 and 6, they all are making 90 degree. Hence, the flux contribution is 0. But in phase 1, here in this phase 1, what is the thing? Surface area is over like this and E is in this direction. E and S are anti-parallel. So, what is the value of theta? It is 180 degree. What is cos 180 degree? It is -1 and hence we get flux due to 1 to be E S cos 180 degree equals to minus of E S. Now, if we see this particular surface number 1, this surface, the right hand surface, this surface vector is also going in this direction and electric flux vector is also going in this direction. So here E and S, this one is for phase 2, backward. This is along the minus x axis, this one is along the positive x axis. So the flux will come around, E and S are parallel and theta equals to 0, cos 0 equals to 1, xi 2 equals to Es. Now xi equals to xi 2 minus 1 in a way, and it will give us E of minus Es, and we will have 2Es. So that is how we are getting 2Es. Now S is surface area equals to S here, which is given by A. So we will replace this surface area as A. So that's how we are getting this particular surface area. Now vectorially we can, okay, the one thing which I aim at telling is, we get one xi as q upon epsilon naught and the other xi as E 2EA. Now we will compare these two. Q will be our sigma into area, this one divided by epsilon equals to 2EA. Here A will cancel out and E will be sigma 2 epsilon naught. So this is what we have got, and this thing we have written vectorically like this: E vector equals to sigma by 2 epsilon naught into the unit vector. Unit vector why we are introducing? Just for the direction. As I have told you multiple times, it is very much necessary for a vector to have both direction as well as magnitude. So whenever we want to define the direction of a vectorial quantity, we will introduce a unit vector. Now similar for the linear, here for the surface area directed away from the plate if this is positive, sigma is positive, and towards the plate if sigma is negative. If it is a positive charge, they will move outwards. E moves outwards. We have seen when we were reading the properties of electric field. And then if it is negative, they will move inwards. So E is independent of x axis also. Here we have seen there is no relation between E and distance. Is there any relation which states that E is proportional to R, 1 by R or 1 by R square or 1 by R cube or anything else? No such relation. So this is independent of x axis. For a finite planar sheet, above equation is approximately true in the middle region of the planar sheets away from the ends. So it is same for the plane as well as the linear. As we have seen, in the middle of it will be less, it will be giving us the most perfect flux. The outer components which are at the end will not be influencing here. Let's move to the third and the last application of Gauss's law. Field due to uniformly charged thin spherical shell. Thin spherical shell we have taken. Thin spherical shell implies that it is a smaller shell where we can take Gaussian surface inside as well as outside. It is not an infinitely long or big or infinite volume spherical shell. Okay, Gaussian surface will be inside and outside. Fields due to uniformly charged thin spherical shell. Let sigma be the uniform surface density of the thin spherical shell of radius capital R. The field at any point P outside or inside can depend only on the R, the distance at where we have taken the Gaussian surface. With the center O, passing through the point P. To the given charged configuration, we have spherical symmetry. From here, if this is the center of sphere, here on the surface, anywhere on the surface, in any dimension, the distance is same, and the amount of charge and the force that charge is facing, everything is same. So that have got the spherical symmetry. Now, as I have already told you, when we are dealing with a thin spherical shell, we have two things to determine over here. When the Gaussian surface we have taken outside the spherical surface, and when the Gaussian surface we have taken inside the spherical surface. Now, first thing, we will go field outside the shell. Now, what we are having is field which is outside the shell. This is our shell. This is blue color is our shell, and this is Gaussian surface. Like this is our Gaussian surface, and this is our shell. So Gaussian surface is present at a r distance from the center. The radius of the Gaussian surface is small r. From the center, whereas radius of the spherical shell is capital R. Consider a point P outside the shell with radius small r. To calculate E at point P, we take Gaussian surface to be sphere of radius small r and with center at O, passing through this point P. E and S at every point are parallel, and flux through each element is E del S. See, if you take a point over here, surface will be in this direction, S, and E will also be in the same direction. So E and S at every point are what? Are parallel. So theta over here is 0 degree. Hence flux equals to ES. And why we have taken del here? Because we are taking such small angles like this. I'll take the contrast color over here. Such small angles like this. Okay. So these are the angles we need to take. That's why we have taken E del S as the flux. Now, summing over all the del S, the flux through the Gaussian surface will be E into 4 pi r square, and the charge enclosed is sigma into 4 pi r square. How does it happen? So I'll explain in the other page. See what we are having. We are having this spherical surface and this as the Gaussian surface. Just painting. This is our thin spherical shell, and this is our Gaussian surface. Okay. So the distance from the center to this is capital R, and from here to here it is R. This is our point P. We have taken small area elements on the surface, Gaussian surface, which are having a value of del S. These small area are del S, and they are directed radially outwards, and the electric field due to the charge over the surface of the thin spherical shell is also in the same direction as del S. E here. So E and del S directed in same direction, same direction. So the flux we get is, flux for one surface we get is E del S1. Similarly, flux for the n elements we get is E del Sn, and when we find the total flux, it comes around E into S. Surface area of sphere is given by 4 pi r square. Why we have taken this square? Because we are dealing with these surfaces. So xi will become E into 4 pi r square. Done. This is one equation for the flux. Now second thing, we know that flux equals to charge upon epsilon naught. Here charge equals to surface charge density into surface area. So here Q will be equals to sigma into 4 pi r square. Why r, capital R? See here, I am taking capital R. Why capital R? Because charge is present on this surface. So this distance should be calculated. The capital R distance should be calculated. Charge is not present over here. That's why it is capital R. So we have got the value of charge to be this. We will substitute this value in this equation. So xi equals to sigma into 4 pi r square divided by epsilon naught. This is our second equation. This is our first equation. Both gives us the value of xi. So xi equals to this xi. It will give us E into 4 pi small r square equals to sigma into 4 pi capital R square divided by epsilon naught. So from here this pi will get cancelled out, and E will be equals to sigma capital R divided by epsilon naught small r square. So this is the electric field at distance small r due to this charged spherical shell. We can write electric field due to charged spherical, which is thin shell, is given in by this formula. Now if we want to introduce the vector, we will introduce vector over here, and we will introduce a r cap. R cap is the direction of the position vector from center to the point P. We are considering E at P. So always make sure to take the small r, not the capital R. Capital R is just for showing the constraints of our charges. The charges are present on the surface of the sphere of radius capital R, but we are calculating at a distance of small r. So by Gauss's law, see over here, the same thing I have done here, which I have already explained you. We are equating it, and the value of E we are getting this value. Now here we have not taken the value of charge. Charge we have taken as such in this way. Q equals to this. If we substitute the value of Q over here, we will find, see, if I just substitute the Q as this, which is given over here, 4 pi r square into sigma divided by 4 pi epsilon naught into small r square. The 4 pi will cancel out, and we will left with sigma r square by epsilon naught r square only. And we have taken the unit vector of small r cap, which is very much necessary to understand. Why we have taken this? Because we are calculating on the Gaussian surface, not on the spherical surface. Now the electric flux is directed outward if charge is positive, Q is greater than 0, and inward if Q is smaller than 0. This is like valid for all the three cases. In the third case also we are reading the same. However, is exactly field produced by the charge Q placed at the center O. Now thus for point outside the shell, the field due to the uniformly charged shell is as if the entire charge of the shell is concentrated on the center. Now whatever answer we are getting, it gives us an idea, like it is just showing us our charge is concentrated, have a concentration at the center of concentration at center of our sphere, Now we will read the other one. Why we are saying this one? Because when we were defining the charge density, we defined charge density at surface. Okay. So now let's go to the last one, where we will see Gaussian surfaces inside the given sphere. Now we need to find the field inside the shell. What is the field inside the shell due to the charge contained by the shell? Now point P, it is a shell, as I saying. What is the difference between a sphere and a shell? Shells are hollow from inside. So the charge, if we are containing at center, it will have distribution over the surface. The charge density will be over the surface. Over surface. The point P is inside the shell. The Gaussian surface is again a sphere through P centered at O. Flux through the Gaussian surface is again same, E cross 4 pi r square. What is flux? Flux is E into S, where S equals to 4 pi r square. Here r is smaller than capital R. In the previous case, small r was bigger than capital R. Gaussian surface encloses no charge. No charge, why? Because charge of a shell is on its surface. So at the center there is no charge present. So E cross 4 pi r square will be equals to 0, and hence the field inside is 0. Field due to the uniformly charged thin shell is 0 at points inside the shell. This important result is a direct consequence of Gauss's law, which follows the Coulomb's law. The experimental verification of this result confirms 1 by r square dependence of the Coulomb's law. Like in this we have made a graph. This thing will be 0, and after this there will be a fall as to the r square. We are moving from the center, there will be reduction in the electric field. So such graph is made for here E is equals to 0, and here E is proportional to 1 by r square. This is a point at center, So this is radius, and here on this axis we define electric field. So this is the relation, graphical relation. So these two last cases, shell cases, when surface is inside, electric field inside and electric field outside, when we are calculating, this defines us this particular phenomena, and it proves the Coulomb's law. It proves 1 by r square dependence of electric field too. So that's all for today's class. Hopefully you understood the application of Gauss's law. It's a very much important topic to understand it. It is very much important to understand which surface is producing flux and why it is producing that much of the flux, why the sign of the flux is negative, why it is a positive in the other case, and why we have taken like some flux is there for the Gaussian surface when the Gaussian surface is outside, and some flux is not there when we have taken the Gaussian surface inside the sphere. I have already explained these topics in this. So kindly just go through this and solve the question like the example or question 11 and 12 which are based on this particular topic to get a clarified view of this topic. So that's all for today's class. We'll meet in the next class with the summary of the chapter. Have a good day. Bye bye.